Hey guys, welcome back. Today we're going to be talking about Newton's first law of motion, which you can see here in its original Latin, which, while certainly very exquisite, most of you probably won't be able to read, and that's certainly to be expected. In its more easy to read, easy to understand state, we have an object at rest remains at rest. An object in motion remains at motion unless acted upon by a non-zero net force. So this is probably a statement that you've all seen in some way, shape, or form at some point. Certainly if you were here for 8th grade, you would have seen it in physical science, hopefully. But what does this mean? So when something is non-zero, then of course that means it has some value, and in this case it may be positive or negative. Net is a term that we're going to use a lot this year. It simply means the total or the sum of all of the, in this case, forces acting on an object. And then force, another word that we're going to be using a lot this entire year, is simply a push or a pull one object exerts on another. And so this is our basic definition of a force, and it's something that we'll come back to over and over again. When talking about force, let's first address the units that are going to be involved. Our basic unit for force is the Newton, named after, of course, Sir Isaac Newton, and the symbol for that is a capital N. Okay, it's a capital N, so we'd have, for instance, 1 Newton would look something like this. When we write our symbol for force in equations, we're going to use a capital F. And one of our most used equations this year that we'll talk about later is going to be F equals ma. So it would look like this in an equation. Now we do have a vast array of different types of forces, and so in order to distinguish between the different types, we're going to use subscripts, similar to how we use subscripts to specify any variable. And so a couple quick examples here, and we'll talk about some more in a minute. The net force, which is what we talked about, the sum or the total of forces, we are going to use F subscript net. So we have a capital F with the subscript net by it, and that tells us the net force. And then another big force, actually it's a small force, relatively speaking, is the gravitational force, and that's going to be F with a subscript g. Now, a few other types of forces. We just mentioned gravity. These here are for what we call fundamental forces, and the fundamental forces are the ones that give rise to everything else, and they're, I guess, maybe the four most important. The first is gravity, and gravity is always going to be an attractive force. It's always a pulling force. It's good for us. It keeps us on the surface of the earth. And it acts between anything that has mass. So any object, no matter how big or small, if it has mass, it's going to exert a gravitational force. And the other kind of interesting thing is that it's an infinite range, or it has an infinite range, which means that we are exerting gravitational forces on the Earth. At the same time, it exerts a gravitational force on us. We are exerting gravitational forces on Jupiter and Neptune and even Pluto and things that are on the other side of the universe. Now, of course, at some point, the effective size of that force becomes insignificant, but that doesn't mean that it's non-existent. Then we have the electromagnetic force, and this is going to be talked about. We'll look at the electrostatic, and then also magnetic. We'll separate these out later in the year, but they all basically come from the same place. The electromagnetic forces can be attractive or repulsive, so that's kind of one way that they're unique from gravity. It's also relatively large. It's bigger than the gravitational force, and it acts between any two charged particles. So where gravity was exerted between anything that had mass, electromagnetic force is between anything that has charge. It also has an infinite range. Then our two maybe lesser known forces are our strong and weak nuclear forces. And these both exist typically within nuclei or within atoms. The strong nuclear force is what keeps the nucleus together. You have all of these protons that have like charges, and they're repelling each other and they're pushing away, and something has to hold them together, overcome that electromagnetic force, and it's the strong nuclear force. It's very, very strong, but it has a very short range, typically about the radius of your average atom, or your average nucleus rather. And then we also have the weak nuclear force, which, as its name would imply, is weaker than the strong nuclear force. This acts between all particles and ultimately is responsible for radioactive decay, which you guys probably talked about in chemistry. A few other types of forces that we're going to be talking about a lot this year that are going to come up, and this is by no means all of the possible forces we might encounter. Tension force, F sub T, is a pulling force. It's typically what happens along ropes or chains, but other things can be put under tension as well. The normal force is a support force, and it's also what we call a reaction force. When you push against a surface, that surface pushes back against you, and that is our normal force. The frictional force is a resistive force, which simply means it acts against the direction of motion, and it always occurs between two surfaces that are in contact with each other. And then we have our elastic force, which is going to be F subscript S, so that we don't confuse it with the electrostatic force. And this is a force that's exerted by any elastic material when it's compressed or stretched. And again, as we talk about each of these or look at each of these more in depth, we'll talk about exactly how they work. So let's go back to that first law then, which is usually called or often called the law of inertia. And the reason for this idea of inertia is an object's natural tendency to resist a change in motion. So resisting a change in its motion, which typically means its velocity, which, as we know, velocity is a vector. So not just necessarily its speed, but also its direction. So inertia, right? Think about it. If we have a 5 kilogram box and a 10 kilogram box, which one is going to be harder to move? And not just get it moving, but also stop it moving. The 10 kilogram box is going to be twice as hard to move or to change the motion of than the 5 kilogram box. Now, inertia doesn't have an actual direct measurement of it, but it's directly related to mass. So if something has twice the mass, it has twice the inertia. More mass, more inertia, less mass, less inertia. So the whole idea behind this first law is that as long as the forces on an object are balanced, as long as there's zero net force, there will be no change in the object's motion. So because an object has this property of inertia, its motion is going to stay the same unless it's acted upon by this net force. So this scenario, this position we're at, where there's zero net force, is what we call mechanical equilibrium. And it's this place where no physical changes occur. And this happens when that net force that we talked about, let's change color here, the net force is zero. Okay, so when the net force is zero, the object is in mechanical equilibrium, and that means that there's no change in its motion. No change in its state of motion, let's say. State of motion. okay? Mathematically, mechanical equilibrium looks like this. Now, this piece, let's break this down. Sigma from math class, sum of, right? F is your forces. 0 means 0, N is our symbol for the unit Newton. So, what this expression here is saying is that mechanical equilibrium occurs when the sum of the forces, the sum of all the forces, is 0. So when we add up all the forces acting on an object, if it's 0, the system's in equilibrium, and if the system's in equilibrium, there's going to be no change in its state of motion. And we're going to use that sum sign a good bit this year as well, so let's keep that in the back of our heads. So, something like this, we have a couple different forces going on, a couple different forces that are in play, and hopefully for our gentleman here hanging on our plank, the system is in mechanical equilibrium. We have a couple of upward forces, which in this case these are strings, so those would be tension forces. Then we have gravitational forces of our painters, and then also the gravitational force of the actual plank itself. And so when we add all of these up, they're going to add up to 0. 0 newtons. So we have our, once again, our FT, FT, FG, FG, and FG. And so our scaffold is in mechanical equilibrium here. Now, how does this all add up to be 0? Well, as we mentioned, forces are vectors, right? So that means that direction matters. And in this case, and again, we've also previously mentioned that we can kind of set our frame of reference however we want. So I'm going to say that up is positive and down is negative, which means that the two tension forces are both positive values, and our 3 gravitational forces are all going to be negative values. So then we would have Ft plus Ft minus Fg minus Fg minus Fg equals 0 newtons. And so that's what that equilibrium piece is going to look like. Everything's balanced. The velocity of our scaffold and the gentleman on it remains 0. And here's what we just said. Now, let's talk a little bit about support forces again, and this is our normal force, right? And this is another very common force. Normal force, whoops, that should be a C, and it's F subscript N, right? So, not F net. Okay, so F net and F normal are 2 separate forces. So let's think about a book that's just lying on your table, or it could be your computer or anything. We know that it must be in mechanical equilibrium because it's not moving, hopefully, but it does have forces acting on it. So pulling that book down is the force of gravity. That's the weight of the book. Now, if that was the only force acting on it, then its motion should be changing because it's a non-zero net force and the system wouldn't be in equilibrium. So what is it that's balancing out the force of gravity? Well, in this case, it's the table pushing up. So as gravity pulls your book or your computer down, it's pushing down on the table. The table is pushing upwards on your book or computer, balancing out the force of gravity. And this is our support force, and this is what we call the normal force. and it's going to be exerted by any surface. If you're leaning against a wall, you're pushing on the wall's pushing back on you. It's keeping you from falling through the wall. When you sit in your chair, you're pushing down on the chair is pushing up on you. Right, so here we have our two forces, and as we said, the force of gravity is acting down on the book. The table is exerting a normal force up on the book, and so Fn minus Fg equals 0, and it's minus because they're in opposite directions, and direction matters. Now, typically we assign up as positive and down as negative. That's what we did in this case. If for some reason you prefer to assign down as positive and up as negative, you're certainly welcome to. Mathematically, it will still work out. Our frame of reference, as long as it's consistent, can be whatever you want. In either case, though, the forces are going to add up to 0, which means that this is true, which means that the system is in mechanical equilibrium and it's not going to change its motion. Another example, standing on a scale. Now you could be standing on a floor, you could be standing on anything. The weight is pulling down, the support force is pushing up, keeping you from falling through the surface. Now, if the physical characteristics of that surface are such that it can't provide enough of a support force, then that's when it breaks. You would break through the table or through the wall or whatever it happens to be. Now let's talk about tension for a moment. Tension occurs anytime, it's actually kind of, it's almost an elastic force, but it's not quite the same because the material tends to not be as elastic. It's something like a rope or a string, or even pieces of metal can be put under tension. And we'll see that in a couple different places. When we talk about weight, weight is a force. It's the force of gravity, right? Force of gravity, which is measured in newtons because it's a force. But when we think about weight, typically, we probably think of it in terms of pounds. Pounds is actually the English unit of force. So when we talk about pounds, we're actually talking about a unit of force. It's just the dirty English system rather than the beautiful metric system. When we use a scale, what we're actually doing is we're using, a spring scale and even some of our other scales use tension, they use elastic forces, they use specific springs to measure the force of gravity. And so when you hang something on a spring scale, such as the one pictured here, and we've actually got some that are similar, but they're going to be round, and they're going to have a little hook, and then there's going to be a dial that goes around this way like that. And we'll look at some of those in class. But when we attach something to the spring scale, the force of gravity pulls it down. It's then exerting a force on the spring inside, which is exerting an elastic force back upward. And it's going to pull until the spring is stretched in such a way that the force of gravity acting down and the elastic force acting up, or the tension acting up, are the same magnitude, and so it hangs there in mechanical equilibrium. Now we'll see here the bag of sugar is 2 pounds, which is roughly 9 newtons. It's not an exact conversion, but it's pretty close. So in this force, and we say tension, elastic, really, but the two are pretty closely tied together. In this case, the two are equal and opposite, so the net force on the bag is 0, so it remains at rest. We're going to look at a lot of other examples here, and and work on determining net forces as well. We'll talk about free body diagrams and a few other things. But for this point, this is everything. I'll see you in class.